lesson on Newton's laws is focusing on Newton's law number 2. If we just remember back to Newton's first law, is that a body continues in a state of rest or uniform velocity unless acted upon by an external or unbalanced force. What we're going to try and do is link in Newton's second law of acceleration into this idea of Newton's first law, because the two of them, in fact all three of the laws, work really well together, and you can interlink them to really describe the mechanical effects of forces on a body. So we talked about, when it came to inertia, we talked about somebody's inertia is the resistance that a body has to change its state of motion. So the greater your inertia, the greater the force that is needed to apply to change that state of motion. So if we were to look at that tennis ball that Andy Murray is about to hit, we know that that tennis ball has got a relatively low inertia. It's not heavy, okay? It's not going to take particularly much to change its state of motion. Okay, whether that is hitting the ball back or serving the ball or throwing it up into the air, you don't have to be particularly strong or apply a very, very big force to make that motion change. Okay, we also looked at this idea of constant velocity. Now that constant velocity can be still or it can be moving. All right, so it doesn't necessarily have to be something that's stationary. That tennis ball is not stationary. There will be a point where it reaches constant velocity. When Mo Farah was running, he can be at constant velocity until an external force acts upon it. And this external force is where we link into Newton's second law. Okay, so Newton's second law is the law of acceleration. Probably one of the most famous ones that he has done. So the law of acceleration states that an object will accelerate proportional to the force acting in the direction of that force. Okay, so body's rate of change in momentum. Right, so there's a key word that we need to think about there. So the change in momentum. Now momentum is the quantity. So we're adding an actual factor into this. It's a quantity of motion. So we're trying to add a numerical concept to motion. Okay, it's very difficult to measure, but momentum is something that we can. And momentum is calculated as mass times velocity. Okay, so somebody's mass multiplied by the velocity. You have to be careful not to interlink it with speed, because it is a different type of measurement, but it's the mass multiplied by the velocity. Okay, so Newton's law, the law of acceleration, is a body's rate of change in momentum, and that is proportional to the size of the force applied, and it acts in the same direction as that force applied. Okay, so it's how quickly it changes its momentum. Okay, so Andy Murray hitting that tennis ball, it's very, very going to quickly change his momentum of that tennis ball, not only because the ball has a very low inertia, so it doesn't have to take much force, but also because of the amount of force that he's applying to it. If you watch any of their games, him versus Federer, so to speak, that the pace of that ball going back and forth, it accelerates very quickly away from that tennis racket. Okay, so if we take our sprinter, we know that he had quite a big mass, so therefore he had a greater motion. So he needs a greater force needed to overcome that inertia and create motion. Okay, overcome that inertia to create motion. All right. So Newton's second law states that the rate of change in momentum, and therefore acceleration, is proportional to the size of the force applied. So that 100-meter sprinter will want to generate as much force, forward force, as possible to accelerate away from the blocks quickly in a forward direction. Okay, so if you think about how a sprinter might look, a sprinter is very muscular, they're very strong, they're very lean. There isn't much wasted mass that sprinter would have, because what they want to do is to be able to lower their weight enough so they've got a lower inertia, but have enough muscle mass and enough muscular force and power so that they're able to accelerate as quickly as they can away from the blocks. Now that forward force is known as friction. So a sprinter will be wearing spikes. They'll be wearing, they'll be running on a very grippy track so that they're able to get that forward force of friction as large as they possibly can. Okay, think of somebody trying to sprint away on a grass track. You know that it's very difficult. A grass slippery track with trainers on. Okay, you know that somebody's going to slip on their face and they're not going to be able to apply enough force to overcome their inertia. So the greater the force applied to that sprinter, the greater rate of change in momentum, and therefore acceleration away from the blocks. The force applied is in a forward direction, and so the sprinter drives forward from the line. Okay, something interesting, if you want to look at this a little bit more, is to look at Usain Bolt. So Usain Bolt, very tall. He's got a quite high mass, so therefore he's got quite a high inertia. And actually, if you watch him race, he's got one of the slowest starts. Okay, so he has one of the slowest starts in a 100-meter race. But when we come to study him a little bit more, we look at the mechanical efficiency of Usain when he gets up and running and he gets up to speed, and he's therefore able to overtake and accelerate more away from the others. But have a look at his sprint start times in comparison to any of the other sprinters that are around, and you'll notice that he has notoriously a very, very slow start. Okay, so Newton's law of acceleration we can apply to this formula, which is force equals mass multiplied by acceleration. So we can actually work out what force is being applied based upon the mass of somebody and the acceleration that they are able to get. Okay. Another key term you need to think about is the fact that acceleration, this rate of change in velocity, is measured in meters per second. Okay, and it is worked out by final velocity minus initial velocity, and I'll put these on a calculation sheet for you to look at. Final velocity minus initial velocity divided by the time. All right, so on this sheet that is going to be just below this video are going to be some calculations for you to do, and then also to work out the rate of change in somebody's velocity. Now, if we were to take a sprint starter, so somebody who's on the blocks, their initial velocity would be 0 because they're not moving. So you take any object that's not moving, their initial velocity is going to be 0. Say their final velocity is at 10 meters per second. So final velocity would be 10 meters per second minus initial velocity, and then you divide that by the time that it is taking. Okay, in the background you can tell I'm working from home because my dogs are starting to bark at this video. Okay, so what we are going to do in a second is I want you to have a look through those calculations, and I want you to have a go at trying to work out somebody's force that is applied in newtons, and then also try and calculate their acceleration. Hopefully that makes sense. Email me back those worksheets when you've managed to do it. Any problems, just drop me an email or on the contact form, it will come through to me. Okay, good luck with Newton's second law of motion.